12.1d, we're going to perform a significance test about the slope of the population of the regression line. So like the confidence interval, we are actually still doing a t-interval, so t-test, for the slope of the least squares regression line. The test statistic, or the t-value for that, for the calculation, is just going to be the sample slope minus our hypothesized parameter of the population slope over the standard error of the slope. Now, keeping in mind, as all hypothesis tests, there's 3 different hypotheses that we could come up with. For the alternative, it might be a greater than test, a less than test, or a two-sided test. Again, for the test, we are going to have to make sure that all the conditions are met, and the conditions are still the same as linear as they were for the confidence interval. I want to go back to the tip data that we looked at the buffet. Here we have the computer output of the results. We have here the residual plot of time and the error related to that, a normal probability plot, and then this right here, don't forget, was our original scatter plot. Again, looking at the computer output, we have the slope, we have the standard error of the slope, we have this test statistic. Now, when we were doing confidence intervals, remember we said ignore the t-value. For the confidence interval, this is not t star. This is the test statistic that we just talked about calculating. So if you use the computer output for linear regression, you must be cautious. That t there is only for the hypothesis test of the slope, not confidence intervals. Now this one here, you want to put a big old star around. The p-value on a linear regression, the value recorded on the computer output is a two-sided test answer. So depending if you're doing a one-sided test or two-sided test, you may have to adjust this data. If we're doing a one-sided test, we can only take half of that value. Let's go ahead and carry out a hypothesis test. Now remember, Charlotte was curious if people stayed longer at the buffet, will they tip more? So will that help us figure out what type of test to do? Is it one-sided or two? For this case, we want to perform a test. Our hypothesis for the null is that beta is 0. If we say the slope is 0, means there's no linear relationship. But she thinks if you spend more time there, you're going to give a higher tip. Therefore, we think it'll be a positive upward slope. We think the relationship between the two variables is positive and increasing. So beta is greater than 0. Let's define beta as the true slope of the population regression line relating length of the stay x to the tip, which is y. And let's choose to use a 5% significance level for alpha. Reference back to the graphs that we saw earlier and check our planned conditions. First thing I do want to do is define the test I'm going to do. So if the conditions are actually met, then we will do a t-test for the slope. In terms of the words, this is really all that we have to state to get credit for our actual test that we've identified. Let's go ahead and look at the linear. Look at the scatter plot and residuals. For the linear condition, the scatter plot shows a weak positive linear relationship between length of stay and tip. The residual plot does look somewhat randomly scattered about the actual residual line of 0. Now for independence, we can assume clearly that one tip shouldn't provide additional information about the other tip. There's definitely going to be some independence in how the tips are related. We are sampling without replacement, so we should go ahead and assume that there are more than 10 times our sample size of 12, so there's more than 120 receipts from this population. For normalcy, look at the normal probability plot, and when you do, you're looking for some nice linear relationship, and it looks roughly linear. For equal variance, I'm going to go back to the actual residual plot and see if there's a nice balanced scatter amongst the x values of 1, 2, 3, 4, and so forth. And for that, the residual plot shows a fairly equal amount of scatter around that residual line of 0. And finally, for randomness, the receipts were randomly selected. Now for the do portion, remember the test statistic is actually on that computer output, but I'm going to show you where it comes from. What they're going to do is take the sample minus our hypothesized beta of 0 over the standard error. So the B estimate and the standard error of B were in the on the computer output, and our hypothesis for the null was 0. That gave us a test statistic of 1.23, which is exactly what they showed, so you can use the computer output. Now, for the p-value, in the computer output is for a two-sided test, so you must cut this in half to get for a one-sided test. Make sure you remember that. If I wanted to find the p-value from the computer output, that's going to be easy enough. I'm just going to take the 0.247 divided by 2. So the computer output p-value is 0.1235. Let me show you though if I wanted to use the Cdf format, because you could for this case. What we're trying to do, remember, our test statistic value was 1.23. We are looking at that the slope is greater than that, so we want this value. So for Cdf, I would do from this test statistic on higher. And for our case, we had 12 in our sample minus 2, so 10 degrees of freedom. If you use the calculator, you will get this as your p-value, which again is exactly half of the computer output. Based on that, we can actually make some conclusions. The p-value is larger than 0.05, so we fail to reject H sub O. Our conclusion, therefore, is we do not have convincing evidence that parties who stay longer at buffets actually leave larger tips. Let's go back to a Chapter 4 type of common follow-up question. They would typically maybe ask you, can we make conclusions about the population or about cause and effect in this case? So think about what we've done. Making conclusions about the population, can we? Yes, they actually used random selection. They randomly selected the tips they were looking at so we can look at the population that's this restaurant. How about cause and effect? No, in this case, there was no random assignment or there was no treatment that was actually assigned. So cause and effect can only be done if a true experiment happens. In this case, Charlotte was just doing an actual study in looking at the observations. Two other key things I just want to highlight in this video. We've already talked about this before, that confidence intervals give more information. Clearly the test just lets us say we reject or fail to reject. The confidence interval can also let us say we reject or fail to reject, but it gives us the values in which we're 95 or 99% confident. I'm going to go back to the Honda examples that we did a long time ago. We had 11 CRVs, and remember they were looking at the number of miles driven and then the advertised price for those. A 95% confidence interval for the slope, so we're looking at the relationship from miles driven and price, which is two quantitative variables so you can compute slope. So this is a really nice example where you could look at the slope and see if there's a relationship. When they did the confidence interval for that, they came up with this is the acceptable slope range at 95% confidence. So here's the question. Based on this interval, what conclusion can we draw about this hypothesis? If they did the test, what they would have said is that the true population slope is 0. But they think the true population slope is different. They are saying that the number of miles does drive price. And recall on the test, they're doing a 5% significance level. So one thing that's good to just keep in mind, if they were doing the test and they were saying it was different, to do a 5% significance level on a test, because it's two-sided here, means we're looking at this tail and this tail. So for 5% alpha, recall that that alpha value at 5% has to be kind of divvied up between the two tails. So really, we're looking at the probability of 0.025 and 0.025. Well, is that consistent with looking at a 95% confidence interval? Absolutely. If we were to construct a 95% confidence interval, we would look in between this range and we would be looking at 95% of the curve. Well, folks, if that's 95% of the curve, 5% more has to be in the tails, which is equally balanced. So these are comparing apples to apples. All right, let's answer the question. How would we make a conclusion about this hypothesis given this confidence interval? Well, when you look at this, the population, we said, parameter is it's equal to 0. Is 0 actually within our confidence interval? In this case, it's not. So what we would say, since 0 is not in the interval of plausible slopes, we can reject H sub O. And based on that, we can make our conclusion. There is convincing evidence of a linear relationship between the number of miles driven and the advertised price. A second reminder, be cautious. If we had said that we failed to reject H sub O, what our conclusion is, we cannot conclude H sub A is true. Be very cautious, never conclude H sub O. Always conclude either H sub A or not H sub A. Now, let's just revisit real quickly the flowers when we looked at the sugar and the freshness of those. They gave us the computer output already, but let's say we had to come up with our own output from it. Let me just show you real quickly to do the test. I'm going to hit Stat Tests, and in this case, if we wanted to do a linear regression test, it would be letter F. Now, I showed you how to do the interval, but here's the test. You're going to go to this screen, and you're going to ask for list 1 and list 2, so I'm going to put the data in list 1 and in list 2. Frequency is just 1. For the freshness, we just wanted to do a two-sided test on that one, so let's do a two-sided test, and then hit Calculate. When you do that, you are going to find here again, this is your test statistic. This is the actual p-value. Let me just confirm back on the computer output. This is the test statistic for the actual slope of sugar, which corresponds with the calculator. Notice the p-value is 0.00. That does correspond with this, but you have to be careful. Remember, scientific notation, so this is really 0.00001, which is close to 0. Degrees of freedom is not stated on the computer output, but we can manually get that. Also notice, let's look back at the slope. Here's the slope from the calculator, 15.2, which we see there. Our y-intercept is 181.2, which we actually see here. Keep in mind this 7.525 we already talked about. What that S is, folks, that is the standard error of the residuals. So the calculator output will not give us the standard error of the slope. So this is not in the calculator output. In double checking their R squared of 86, that's exactly what we have too. So that's how you can relate computer output to the calculator output for a linear regression test.